Hello again. So in this video, we're going to look at the chain rule again, but we're going to write it in a different way. And this way of writing the chain rule tends to have different use cases than what we've already seen. Suppose Suppose a drop of water hits a pond. Then that drop of water is going to form a circular ripple, and the ripple is going to expand. The ripple is going to go out from the center. So the ripple is expanding. In this situation, let me write down two functions or two equations. This ripple has a radius, and this circle has an area. So a perhaps familiar equation A equals pi r squared. But the radius is not constant here. The radius is changing with time. The area depends on the radius, but the radius depends on time. And I'm not going to worry if this equation is super realistic. Let's just set one up. Maybe the radius is t plus 1/2 the square root of t. And I guess we ought to have units here. T can be measured in seconds. R can be measured in inches. Well, if the area depends on the radius, and the radius depends on the time, then the area indirectly depends on the time as well. And as time passes, the area changes. And you can ask, what's the derivative of the area with respect to time? Well, we already have all of the, and let me point out, I mean, we have two equations. Neither, if we could take the derivative of A, we could take the derivative of R. Neither of those is what we're asking about. If we took the derivative of the first equation, we'd get to dA dr, the derivative of the area with respect to the radius. If we took the derivative of the second equation, we'd get to dr dt, the derivative of the radius with respect to time. Neither of these are the derivative I asked for. Neither of these are dA dt. So the sort of topic of the video is, how do we find dA dt? And the answer to that lies in the chain rule. Because the chain rule is a method for dealing with compositions. And even though we don't have function notation here, we don't have, composition notation. If A depends on R and R depends on T, then we can do a composition, function notation or not. If A equals pi r squared, and r is t plus 1/2 the square root of t, then A is pi times t plus 1/2 the square root of t squared. And this is just what we need for the derivative we asked about. We wanted the derivative of A with respect to time. Well, now we have A written with respect to time. dA dt equals 2 times pi times t plus 1/2 the square root of t raised to the first power times 1 plus 1/4 the square root of t. We can find this derivative using the generalized power rule, which is just a special case of the chain rule. Does anything here need special note? Remember that when you take the derivative of the square root, you get a 1/2, and we already had a 1/2, and that's why we end up with a 1/4. Otherwise, we're just using the power. So we found dA dt, but I can't say there was no muss, no fuss. To find dA dt, we had to create a third equation. We started with two equations. We started with A equals pi r squared and r equals t plus 1/2 the square root of t. Neither of those equations, when we took their derivatives, gave us the derivative we wanted. For the derivative we wanted, dA dt, we had to create a third equation, which certainly wasn't the end of the world. But the version of the chain rule we're going to look at now would have allowed us to find dA dt without creating a third equation. The chain rule, when you are using Leibniz notation, says that if y depends on x and x depends on t, then dy dt is the product of dy dx times dx dt. This is the chain rule. It's just written using Leibniz notation. And I'd like to come back to this problem, but before I do, let me just do a quick first example. Say that y equals the square root of x and x equals t squared plus t plus 1. And we want dy dt. Y depends on x and x depends on t, so y depends on t. And it makes sense to ask for this derivative. Well, we can find dy dx, the derivative of y with respect to x. It's 1 over 2 the square root of x. And we can find dx dt, the derivative of x with respect to t. It's 2t plus 1. And this version of the chain rule says, neither of these derivatives are the derivative I want, but this version of the chain rule says to find the derivative I want, I can just take these two derivatives and multiply them together. 1 over 2 the square root of x times 2t plus 1. Now, something kind of wonky has happened here. Dy dt, the derivative of y with respect to t, is now written in terms of two different variables. It's written in terms of t, but it's also written in terms of x. Well, fortunately, we know that x is t squared plus t plus 1, so we can just do a substitution. This is 1 over 2 times the square root of t squared plus t plus 1 all times 2t plus 1. So we found the derivative we want. We multiplied the two derivatives together, and then we did a substitution. Let's go back to the drop of water, hitting a pond and creating a ripple. I asked for dA dt, and I found dA dt, but in order to do that, I had to create a new function. A equals pi times t plus 1/2 the square root of t squared. So, on the one hand, it's hardly the end of the world, but it is additional labor that I did that I didn't have to do. Because this version of the chain rule, with A's and R's instead of Y's and X's, says that dA dt equals dA dr times dr dt. This version of the chain rule says, well, neither of the derivatives I can take are the one I'm asking about, but the derivative I'm asking about is just the product of these derivatives. Well, dA dt, do not get tripped up by the pi. The pi is a constant. It just sits there. dA dr, we find using the power rule on pi r squared, we get 2 times pi times r to the first. dr dt is 1 plus 1 over 4 the square root of t. Now, let me get rid of that first, because it's not doing anything. R is t plus 1 over 2, the square root of t. So we're going to take this and we're going to plug that value of r right in. And we end up with 2 times pi times t plus 1 over the 1/2 the square root of t times this 1 plus 1 over 4 the square root of t. And I cleverly scribbled this out, but I didn't scribble it out so badly that you can't see. This is the derivative that we got earlier. But the first time we got the derivative, we had to write this intermediate step. Here, there are no intermediate steps. We just took the derivative directly using this version of the chain rule.